So in this video, we're going to talk about the Poisson distribution. So in particular, we're going to be interested in counting the number of occurrences of something over a fixed interval. So maybe you're going to count how many people come into a bank during a certain time period, or on a fixed stretch of road, maybe you're going to count the number of potholes or seam buckling or those kinds of things. So we refer to a random variable as an approximate Poisson process with parameter lambda if the number of occurrences from different non-overlapping time intervals are independent. So like the people arriving into a bank, one person going to a bank most likely has no effect on another person going into a bank or when they go in. There's a sufficiently small sufficiently small interval so that the probability of exactly one occurrence is the parameter times the length of the interval. So the idea here is that you can make the time interval small enough to where at most one person goes into the bank at that time. You can make this time interval small enough. So that's what the next part says. The probability of two or more occurrences in a sufficiently short time interval is approximately 0. So you can chop up your interval into small enough pieces so that there's only 0 or 1 occurrences in any given one of those small intervals. Okay. So what we're assuming things is like two people don't go into the bank at the exact same time. All right. So let's suppose we have an approximate Poisson process. By probability B, we can cut down our interval into n pieces, so of length 1 over n, so that the probability of any occurrence is lambda times 1 over n. Okay. So these pieces certainly don't overlap. The occurrences are independent, and the probability that each occurrence happens is identical for each interval. Each of them is lambda times 1 over n. So they're independent. The probability stays the same, and we're going to do these think of them as trials, doing them over and over and over again. And again, the probability that two or more can happen is 0. So we can think of this as a sequence of Bernoulli trials. N is the number of trials. Lambda over n is the probability of success. So let's see what we have. From our binomial distribution, it's an approximation here because we're using the binomial to approximate the probability. So we have n choose x, so this is just our formula for n choose x. Lambda to the x over n, or lambda to the n over x, sorry. Try that again. Lambda over n to the x times 1 minus lambda over n to the n minus x. This is just our PMF for the binomial distribution. Now let's let n go to infinity, because we're going to chop this up into smaller and smaller and smaller pieces. You've done this kind of thing in calculus. Alright, so the first thing we're going to do is we're going to rewrite this expression here and move some things around. Okay, so I'm going to take the x factorial, and I'm going to put it with the lambda to the x here. So that's what this second term is. If we write out n factorial, we'll have n times n minus 1 times n minus 2 all the way down to 1. But at some point we hit n minus x and go all the way down to 1. When we do that, that cancels out with the n minus x factorial on bottom, which is why we're just left with n times n minus 1 down to n minus x plus 1. And then this last term we're just going to break into two pieces. Alright, so now notice that there are x factors on top, because we started with subtracting off 0 and then subtract off x but add 1 back. So there's x factors on top. I've got x factors of n on bottom, so I can break that up into several pieces. And then I'm going to take the limit of a product, it's the product of the limits, so just breaking it up over those 4 pieces. Now let's analyze what each limit is. Each of these, since there's an n on top and an n on bottom, each of these fractions goes to 1. The second term, there are no n's, so it's just lambda to the x over x factorial. The third one we should recognize as a special limit. This goes to e to the negative lambda. And the fourth one, this one goes to 0 again, and it's the inside, so this just goes 1 to the minus x, which is just 1. So here is what we get as n goes to infinity for the probability that x equals x. So this now is our PMF for the Poisson distribution. So for the PMF, or the Poisson distribution with parameter lambda, is f of x equals lambda to the x, e to the minus lambda over x factorial. And now x can be 0, 1, 2, and so on. We have this infinite support here, infinite discrete support here for the Poisson distribution. Okay, let's show that this really is a PMF. And this is not too bad if you remember stuff from power series. The Maclaurin series for e to the x is this expression. So if I put lambda into this, I get e to the lambda. Right? If I put lambda into the right-hand side, I get e to the lambda. So here's the PMF for the Poisson distribution. E to the minus lambda has no x's, so I can factor it out in front, and then I see the exact form here, where the x has been replaced with lambda, and now x is playing the role of n. So I get e to the minus lambda times e to the lambda, which does give me 1. We can also do the moment generating function. We talked about this before. So if we do expected value of e to the tx, well, here is e to the tx times our PMF. So now let's put pieces together. I've got e to the t raised to the x power, so I'll combine it with the lambda. And again, we'll factor out to the e to the minus lambda out in front. Now this, looking here, we see that it's lambda e to the t that's been replaced for the x that would be up here. So this is e to the minus lambda, e to the lambda e to the t, which simplifies to e to the lambda times e to the t minus 1. So this is the moment generating function for the Poisson distribution. Now, using the moment generating function, we've seen how we can find mean and variance. First, we'll take the derivative of this function. Derivative of e to a power is e to that power times the derivative of the power. For the second derivative, we'll have to use the product rule. Here's the first function. Its derivative is this piece times the second. And then it's plus first times the derivative of the second. Well, derivative of e to the t is just itself. Now let's do the values. First derivative evaluated at 0. We get e to the 0 is 1. That makes a 0 here, so we get an e to the 0, which is 1, times lambda times 1. So we get lambda. Second derivative evaluated at 0, putting in 0 for all of these t's. This becomes 0, so this is a 1. This is a 1. This is a 1. This is a 1, and this is a 1. So all we're left with are these two lambdas, which gives us the lambda squared, and this lambda here. So we get lambda squared plus lambda. So the mean is just lambda, and the variance is lambda squared plus lambda minus lambda squared, or just lambda. So for the Poisson distribution, we notice that the mean and the variance are equal to each other. So let's do a quick example here. Let's suppose that x is a Poisson distribution, has a mean of 4. Let's find the probability that x is between 1 and 3, and the probability that x is actually greater than 3. Lambda is 4 in this case, so here's our PMF. For part A, if we want between 1 and 3 inclusive, we'll plug in 1, we'll plug in 2, we'll plug in 3, and add them together. That gives you that value, 68 thirds e to the negative 4th. And if you really want to get a decimal, you can. Go plug it into a calculator. Let's look at part B. Well, this is 3 or greater, so it means we have to do 3 or 4 or 5 or 6, and so on. That's an infinite sum. That's hard. So let's change it to 1 minus the probability that's less than or equal to 2. So that would be 0, 1, or 2. So we plug in 0, we plug in 1, we plug in 2, add them together, subtract the result from 1, and gives us 1 minus 13 e to the 4th. So there's an example of how we can use using the Poisson distribution, and we'll talk about some more application problems with Poisson distribution in class.